Good afternoon to all. This is an experiment used to measure the attenuation loss, bending loss and optical numerical aperture of the optical cable. So what is optical cable? Optical cable is a wired channel which is connected between the transmitter and receiver in a optical fiber communication. So in this block diagram we can see the input signal, information signal in the form of sine wave will be transmitted through optical cable by converting electrical energy in the form of analog or digital into a optical signal, and it will be transmitted through the optical cable, and at the receiver end this will be converted back into electrical signal by using phototransistor, and it will be transmitted to the receiver end. So here the same block diagram is represented in this kit where input signal 1 kilohertz sinusoidal signal is connected to the emitter circuit. So this emitter circuit, it acts as a transmitter where information signal in the form of analog signal will convert into a light signal through this LED. LED is a emitter circuit which converts electrical signal into a optical signal. And this optical signal will be again given to the detector circuit, where detector is a phototransistor which converts optical signal or light signal back into a electrical signal, and will observe the output at the detector end. So in this first experiment we need to measure the attenuation loss of a optical signal. So optical signal, optical cable actually it is made up of glass material and which contains core and cladding layer within it. Actually based on the total internal reflection, light signal is transmitted through the core part of the cable, but still completely it is total internal reflection and totally it should be confined within the core of the cable. Still there will be some losses like attenuation loss, bending loss will occur in the optical cable. So let us measure the attenuation loss using two cable. We have two length of cable, one is 0.5 millimeter length and one more 1 meter length. So first initially I will connect optical cable with a 0.5 meter and we will observe the output signal, and let us consider that output voltage as V1. The formula for calculating the attenuation loss is V1 by V2 is equal to e to the power minus alpha into L1 plus L2, where alpha represent attenuation loss. It is measured in Nepers per meter. So V1 means whatever the voltage available at the detector for 0.5 meter. So I have connected all the connection and power supply also given to the kit, and let us connect the probe of CRO to the detector and we'll observe the output voltage as V1 for 0.5 meter cable. So in this CRO we can observe for 0.5 meter cable the output voltage is 1 into 5 volt. So V1 is equal to 5 volt. And now second step, to measure the attenuation loss we want V2 voltage also. V2 will be obtained by replacing the previous optical cable by 1 meter cable. So the second cable is 1 meter cable, and we will observe the output voltage for 1 meter cable. Concept behind this experiment is, as you increase the length of the optical cable, the losses will increase, so that voltage must decrease. So now you can observe the output voltage, it is not equal to 5 volt, now it has changed to instead of 1 volt, now it has changed to 0.7 volt. 0.7 volt into 5, you are getting around 3.5 volt, V2. Okay, so we got V1 voltage as 5 volt V1 as 5 volt, V2 as 3.5 volt. Because of the length, as the length increases, the voltage decreases. Now we need to substitute in the equation e to the power minus alpha into L1 0.5 meter plus L2 1 meter. So we will be getting the alpha value is equal to 0.1026 nepers per meter. This is the attenuation loss. Actually, even though the attenuation loss is present in the optical fiber cable, but it is very less compared to all coaxial cable, other cables. But it is around 0.1 nepers per meter is obtained. This is the one part of the experiment. Second part of the experiment, we need to calculate the bending loss. Bending loss will be calculated by rotating the 1 meter cable through the mandrel. So that as you increase the radius of curvature, as you increase the number of turns, the losses will increase. So let us do the experiment by using 1 meter cable. See, 1 meter cable, I am not changing any setting of this connection. I have taken the 1 meter cable and we need to rotate this cable over a mandrel. I will rotate one turn and let us take the output voltage for one turn. For one turn, it is around 1.4 into 2. So 2.8 volt for one turn. One turn 2.8 volt. Now we will repeat the next step. Let us consider as X 2.8 volt, 2.4 volt. Next, if I rotate the next number of turn, second turn, and observe the output voltage. See, it has reduced. Initially it was 1.4 or 1.5 into 2. Now it is less than 2.4 volt. So as you increase the number of turns, the voltage value will be decreases. So bending loss will be calculated by X minus Y. X minus Y means the first voltage minus second voltage. That difference will give the bending loss. Okay, so the thing here, the concept behind the bending loss, as you increase the number of turns or the radius of curvature is increases, there will be a losses in the optical signal. Actually, whatever the light signal transmitted through the core will pass towards the cladding, so that there will be a losses in the output signal. And the last part of the experiment is to calculate the numerical aperture. What do you mean by numerical aperture? Numerical aperture means the degree in which the light will travels through the core part of the cable. So what do you mean by core part of the cable? So actually, what is the light gathering capacity of the optical cable will be measured as a numerical aperture. Also it can be calculated in terms of theta angle. Here actually we are taking one scale. Actually it will be measured using the numerical measurement, numerical aperture measurement jig, which contains one scale and the white screen which contains many circles. The innermost circle diameter is 10 millimeter, then 15 millimeter, 20 millimeter, like that. And here the procedure for calculating the numerical aperture, the formula is this one. NA is equal to W divided by 4L square plus W square whole to the power 0.5. So W means width of the circle, and L means what is the length. Actually we are moving this white screen towards the scale, so that the whatever the light signal should it should cover the particular circle. So that L means length within the scale, width means what is the circle width. So we will connect this cable, 1 meter cable, at one end of this jig, and we are taking the circle 10 meter and 15 meter diameter of the circle, and we are changing the just we are moving this white screen, and we should keep the white screen perpendicular to the axis of the scale, and we should move this circle so that initially it must cover the innermost circle with the width 10 millimeter. Okay, so for numerical aperture, the 10 millimeter with the length 10 millimeter, the innermost circle will be covered with the scale. It is measured, length is measured in the centimeter. It comes around 1.7 centimeter. Here it should be keep it perpendicular to each other, so that the first 10 millimeter circle is covered at 1.7 centimeter distance. So that should be taken as L value. Again, next step, that will be considered as a L1 for one reading. So diameter W in 10 millimeter, and this scale size is 1.7 centimeter. Later again we should move the white screen further, so that the second circle 50 millimeter diameter should be covered, and it is around 2.53 centimeter, and the length is 2.5 centimeter, and width is 15 millimeter. And after that we should substitute in this equation numerical aperture, and that will be the numerical aperture of the optical cable. So numerical aperture means it is a light gathering capacity of the optical cable, and also we can calculate numerical aperture is equal to sin theta, and theta angle also gives what is the angle in which light should be entered within the optical cable. So this is the regarding the optical fibers and how to measure the different parameter within the optical cable. So that this is it is an example for wired communication in a optical fiber communication. Thank you.